Welcome to Lesson 13a, Blasius-boundary layer displacement thickness. In this lesson, we define displacement thickness for a boundary layer and talk about some of its effects. Then we'll generate an equation for displacement thickness for the Blasius flat plate boundary layer. Finally, I'll discuss an iterative procedure for boundary layer analysis where we apply corrections due to displacement thickness. As a quick review, here are the boundary layer equations and the step-by-step solution procedure. In previous lessons, we did the first 3 steps for a flat plate boundary layer, the Blasius solution, where the flow was steady and U is a constant. We obtained a similarity solution. With these similarity variables, our similarity equation, a third-order ODE, and boundary conditions, we solved using the Runge-Kutta technique with arbitrary constant C equal 1/2. Now let's start doing step 4. In other words, we'll calculate some quantities of interest in this boundary layer. I used MATLAB and the Runge-Kutta technique to solve the differential equation, and these are columns of eta, f double prime, f prime, and f, remembering that f prime is u over capital U. The first thing we can find is the Blasius boundary layer thickness delta. By convention, we define delta, or sometimes delta 99, as the y location, where u is 99% of the outer flow speed capital U, or u equals 0.99 capital U. So let's look for the location where this happens, where this is f prime or u over u, and note that I'm skipping lots of rows here because there are hundreds of them. But we see this location where f prime is 0.99025, so somewhere between these two eta values is our 99% value. So let's interpolate. To 3 digits I get eta equal 4.91 when u equal 0.99 capital U. This is thus related to our delta, which we can find by writing the equation for eta and knowing that at y equal delta, eta equal 4.91. Plugging in this y and this eta and doing a little algebra, we get that delta is 4.91 square root of nu x over u, which tells us that delta grows like square root of x, which we already had pointed out. Or, non-dimensionally, delta over x is approximately 4.91 square root of nu over ux, or delta over x is approximately 4.91 over the square root of rex. This is our expression for delta, the 99% boundary layer thickness for a flat plate, and we're assuming laminar flow, of course. Before I continue, let's complete step 5 of our procedure, which is to verify that the boundary layer is thin. Let's do a quick example. If we have a flat plate and we're looking 1 meter down the plate with a free stream speed of 10 meters per second in air, how thick is the boundary layer at 1 meter down the plate? Well, rex is ux over nu, which turns out to be about 6.7 times 10 to the 5th. And then from our equation, delta equal x times 4.91 over the square root of rex. And when we plug in x equal 1 meter, we get 6.0 times 10 to the minus 3 meters, or 6 millimeters. So we can say that yes, delta is very small compared to x for this example, namely 6 millimeters compared to 1 meter. I note that this is a fairly high Reynolds number for laminar flow. The actual flow would probably be transitional at this downstream location. Now let's go back to step 4 and define some other parameters of interest. In particular, let's talk about displacement thickness delta star. By definition, it's the distance that streamlines outside the boundary layer are displaced, hence the name, away from the wall. I'll try to carefully sketch this for our Blasius flat plate boundary layer. Again, I'll greatly exaggerate delta for instructional purposes. Upstream of the plate, we have a uniform flow of speed u, but at some x location in the boundary layer, our profile looks something like this, where the boundary layer asymptotes to capital U outside the boundary layer. Now let's plot some streamlines. I note first of all that this streamline does not go outside the boundary layer like that, which a lot of students would draw. Rather, the streamline right along the wall just stays flat along the wall. The one above that one is displaced a little bit upward, and these streamlines pass through delta. If we consider a streamline outside the boundary layer, it displaces upward something like that, and if I compare to a horizontal line, this displacement is what we call delta star, which is a function of x. It's the distance that streamlines outside the boundary layer, such as this one, are displaced upward away from the wall. Why are they deflected upward or displaced? It's simply a matter of conservation of mass. Compared to the flow coming in, this boundary layer, for the same height, does not carry its fair share of the volume flow rate. So the flow must displace upward, such that the volume flow rate here is the same as that here. Here's an alternate definition of delta star, or a different way of looking at it. Think of it as the amount you would have to displace or thicken the wall to get an equivalent mass flow rate in a hypothetical frictionless flow above the wall at some x location, which I should have set up here, since delta star is a function of x. I'll explain this definition with the diagram, where I'll compare the real or actual flow to the hypothetical frictionless flow that I mentioned here in the definition. At some x location, where this is the wall, the real boundary layer looks like this, and consider some height h above delta, where delta would be somewhere around here, the 99% value. Delta star would be this thickness, which as we'll see is smaller than delta. Well, we can calculate some mass flow rate here, or mass flow rate per unit depth into the page, since we know this boundary layer profile shape. And for the hypothetical frictionless flow, we need to get an equivalent mass flow rate with a displaced imaginary wall displaced by displacement thickness delta star, and at the same h in a frictionless flow, the velocity profile would be uniform at capital U. If this mass flow rate is the same as our real case, this displaced wall is defined as our displacement thickness. In other words, the wall is effectively thicker due to the displacement thickness effect. Now we see the importance of a thin boundary layer, recalling that we defined the boundary layer as being so thin that you can barely even see it, such that it does not affect the outer flow. If delta were not thin, which happens if you have a small Reynolds number, the boundary layer would be thick, and let's draw it on both sides in these cases. And because of the displacement effect, this flat plate appears to be thicker by this amount delta star, and instead of U outside the boundary layer being uniform, our irrotational outer flow would have to compensate by overshooting near the wall. Thus the assumption or approximation that U remains constant above the boundary layer is no longer valid, since we effectively see a thicker plate, and the flow must accelerate to compensate for this thickness. Then our potential flow solution or irrotational outer flow solution would break down. You'd have to solve it for this body shape. In other words, capital U would depend on x and would not be a constant. We can actually use displacement thickness and this concept of a thicker wall to analyze our boundary layers with a correction for displacement thickness. Consider a more practical body like an airfoil in a free stream, where x is measured from the stagnation point and capital U is a function of x. Here's a procedure to account for displacement thickness. First, you calculate U of x based on the actual body shape using potential flow. You assume a thin boundary layer and solve the boundary layer equations, and when you're done, you generate delta star of x. Then you add this delta star to the body. In other words, you thicken the body by delta star of x. Then you calculate U of x on this thicker or displaced body, and then redo the boundary layer solution. You can then repeat this a few times until convergence. But I note that you must always add delta star to the original body every time you repeat this procedure. You don't keep adding delta star above itself. You add it to the original body. Otherwise, your procedure will not converge. You'll just get a fatter and fatter body. I used to do this procedure with the boundary layer code when I worked at the Garfield-Thomas Water Tunnel as an undergraduate student. Now let's generate an expression for delta star for the Blasius boundary layer case. From the next lesson in this series, I'll derive the equation for delta star for a general boundary layer as the integral from 0 to infinity 1 minus u over u dy. For now, let's just take this as a given equation. For the Blasius case, Let's integrate, where we need to convert to our similarity variables. Well, u over u is f prime, and since eta is y, square root of u over nu x, for the case with c equal 1/2, dy is square root of nu x over u d eta. And our limits of integration go from eta equals 0 at y equals 0 to eta equal infinity at y equal infinity. Thus, delta star is the square root of nu x over u, since none of these need to stay inside the integral. Integral from eta equals 0 to infinity, 1 minus f prime d eta. Well, this is a simple integral, namely eta minus f, evaluated from 0 to infinity. But at the lower limit of eta equals 0, both f and eta are 0, so this part goes away, and we end up with delta star is the square root of nu x over u, eta minus f, evaluated at infinity. Well, how do we get this? Well, we'll look at our table from the Runge-Kutta solution. It turns out that the quantity eta minus f approaches a constant as eta approaches infinity. That's because f prime approaches a constant, which is 1, as eta goes to infinity. Therefore, f grows linearly with eta as eta approaches infinity. So since both f and eta grow linearly with eta, eta minus f must approach a constant. Here's our Blasius solution from our MATLAB code again, and I skipped all the way to the end, where remember that we set eta equal to infinity at eta of 10. Again, this column is eta, and this last column is f. So eta minus f at infinity is eta at infinity, 10, minus f at infinity, or this number, and I won't include all the digits, but we get 1.72 roughly. So we can plug this into our equation for delta star. How do you know if your infinity is big enough, bro? Great question, Arlo. Let's try a different eta value, where eta is not quite at 10. Let's take this eta minus this f. So at this eta minus this f, we get the same value. In other words, the quantity eta minus f approaches a constant as eta goes to infinity. Far out, man. Yes, far out indeed, Arlo. So finally, coming back to our equation for delta star for the Blasius flat plate, which I repeat here, we let this be our 1.72074 value, or we get delta star over x is about 1.72 over square root of Reynolds number based on x. Finally, compared to delta, which has the same expression but a different numerator, we see that delta star is approximately 1/3 the thickness of delta for the Blasius boundary layer. Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3.